everyone. Let's start lecture 12. So, this equation comes out to be another TEFL equation for I would say this particular line. We have already mentioned this line we are considering, which is the parallel line of the individual TEFL lines for hydrogen evolution reaction on zinc surface as well as platinum surface, and here neta c is nothing but neta c prime is nothing but this. So, this is the neta c prime. So, and here it is the total IC of hydrogen evolution, which is nothing but the addition of two current densities corresponding to hydrogen evolution reaction for on zinc as well as platinum surface, and this is nothing but the over voltage, and here this E core is nothing but the E mix. So, we have mentioned that if we consider this particular plot, so this is the new E mix. So, instead of E core I can write E mix I can write. I should write it in black. E mix. Now, this equation 2, let us say, and this is equation 1, this equation, this becomes this is one equation. So, this is the equation 1, and let me find out one more equation for this one. So, the equation becomes neta A prime equal to E mix minus E equilibrium of zinc. So, this is E equilibrium of zinc. So, I am considering this much polarization equal to beta C, beta A log of I A divided by I 0 zinc over zinc surface. If we see, so this is, we are considering this line. Okay. So, this is the equation. Now, one thing is very clear from this, that at this mixed potential point I can say equal to I A, which is valid for this point, this is valid. So, in fact, I can write it to be that means this is equation 2, which I can simplify minus 0.659 equal to 0.1 log of I A and I A minus 0.1 log of 10 to the power minus 9, because this value is 10 to the power minus 9. So, it becomes E mix plus 0.659 equal to 0.1 log of I A minus 0.1, or I can say this is plus 0.9. This is equation or let us say, let me put this one as equation 2, and from the equation 1 I can write E mix plus 0.059 equal to minus 0.1 log of IC total, or let me put the same notation. This is the notation we have used, hydrogen total divided by I0 hydrogen. The notation what we have used is basically the total again over zinc platinum. So, I used plus, so this is plus. So, that means this I0 is the addition of this particular current density and this particular current density, which is giving this current density. So, now I have seen that at this mixed potential point I can have this condition meeting. So, I can easily write this is to be minus 0.1 log of IA plus 0.1 log of 10 to the power minus 5, since we have seen that this value, which is the I0 total hydrogen, is nothing but 10 to the minus 5 ampere. So, ampere per centimeter square. So, this becomes E mix plus 0.059 equal to minus 0.1 log of IA minus 0.5. So, this let us say equation 3. So, then by adding equation 1 and 2, and this current density and this current density are same, since IC hydrogen total equal to IA at E mix. So, now if we add equation 2 and 3, we get 2 E mix plus 0.718 equal to 0.4. So, E mix equal to minus 0.318 divided by 2 equal to 0.159 volt. So, E mix turns out to be this E mix, this value turns out to be 0.159 volt. Now, once we know E mix, we wanted to find out I got zinc when the platinum is present. So, now we have to find out IA, this IA I have to find out. So, once we know, we can use using equation 2. So, I put those values 0.159 plus 0.659 equal to 0.1 log of IA plus 0.9. So, we are getting this is 0.5 0.1 plus 0.1 log of IA plus 0.9. So, I am getting IA to be 10 to the power minus 4 ampere centimeter square. When zinc is connected galvanically with platinum, where I0 equal to 10 to the power minus 5 ampere per centimeter square. So, it is very clear that I am having, if without galvanic coupling, my corrosion rate was 10 to the power minus 7 ampere per centimeter square, and now after coupling. So, what was without coupling? So, I A, and in fact, this is nothing but I core when platinum is connected, and I core when platinum is not there is equal to 10 to the power minus 7. So, there is order of magnitude increase in the corrosion rate when an active metal is connected to a noble metal with much higher exchange current density of hydrogen evolution on that noble metal surface, and also the E mix moves up. That means, if we see this, the E core when platinum was not there. So, E core was positioned here, but after it is connected to platinum with higher exchange current density of hydrogen evolution on that surface, the corrosion potential or the E core or E mix has moved up, but the corrosion rate of that active component, that is zinc, has gone up orders of magnitude. So, this is one numerical problem which talks about how we can get all those values. In fact, now these two values one can easily find out, though we will not do it here, I am leaving it to you, because now if we see this particular line which is the E core line, and now that line cuts the hydrogen evolution reaction on zinc surface at this point, and hydrogen evolution reaction on the platinum surface at this point. In fact, this reaction is hydrogen on zinc, and this point is I0. So, it is IC, hydrogen reaction on platinum. So, these 2 points can be easily found out. How? We have to just consider this line for finding out this particular current density, and that time my over voltage would be prime. Similar over voltage will have to be applied for this particular line. So, then you will get both those current densities. So, this is about a situation when we connect an active component with a noble metal with a higher exchange current density of the cathodic reactions over that noble metal, and then we see that how the corrosion potential as well as corrosion current density increases. And our topic, of course, we are continuing our discussion on explanation of corrosion event on the basis of mixed potential theory. And today we will consider a situation which talks about area effect of the cathodic and anodic component. So, when we have a kind of electrochemical reaction like dissolution of active component, we have already seen from the discussion in lecture 10 and 11 that the exchange current density has got a huge implication on the rate of corrosion of the active component. and the exchange current density over the noble component in that galvanic coupling does play a huge role. We have shown an example the exchange current density of hydrogen evolution on platinum and zinc surface, and then how the zinc corrosion rate increases manifold, and also the E mix or the new corrosion potential moves up as compared to the situation where zinc is not galvanically connected to platinum, and we have solved one numerical problem. Now, in this case we will see a situation where let us say one active component is connected to galvanically connected to a noble component in a practical situation, and copper and iron, where iron rivet loses its strength if that rivet is used to join two copper plates. And there one situation is of course the exchange current density over that cathodic component of that cathodic reaction could be high, and at the same time area of the cathode in a situation where let us say the example what we have mentioned before, that copper plate and iron rivet. So, the cathodic component area is much higher than the area of the anodic component when both are exposed to corrosive. So, we need to discuss that part, and we will also try to solve one numerical problem and try to see how the corrosion rate as well as corrosion potential change. Now, we have already seen this example. Let us draw this. This example we have seen, this is E in volt, and of course, we are talking about with reference to SHE, it is standard hydrogen electrode. Now, if platinum and zinc we have considered, no, isn't it, in the last class, where this is the couple, and we are talking about acid medium of certain pH. Depending on the pH, I can have equilibrium hydrogen, and we have already seen that the corrosion rate so now this is the combination. So, this is I0 hydrogen over zinc, this is I0 hydrogen over platinum, and this is nothing but I0 total equal to I0 hydrogen over zinc and plus I0 hydrogen over platinum, and this point is I0 zinc over zinc surface, and this is E equilibrium zinc. Now, when you extend it, so this becomes my new E mix, and this was the corrosion rate earlier. This is E core when platinum not connected, this is platinum connected, and the corrosion rate also changes. This is I core equal to IA when platinum not there, and this is I core equal to IA equal to when platinum is connected. So, these are the differences, we have seen this, but both the cases this area was 1 centimeter square, this was also 1 centimeter square. That means the zinc, this is for zinc, this is for platinum. So, that means equal area were galvanically connected. Now, if area of the platinum increases in comparison to zinc, so that means A platinum is more than A zinc. So, then what would happen? So, let us say that we take 100 centimeter square of platinum and 1 centimeter square of zinc. Now, this green line is for 1 centimeter square galvanic couple. So, this particular line indicates platinum and zinc both at 1 centimeter square. So, now we need to see what happens if we increase the platinum area 100 times as compared to zinc. So, this is the log I scale, this is the log I, and which is ampere per centimeter square. Now, if the platinum surface is not changed, it remains same, the solution remains same, all the conditions remain same, only change is the area of the platinum. So, if area of the platinum increases, so would we think that the exchange current density of hydrogen evolution on the platinum would change? No, it will not change, it will remain same. So, if it remains same, so then whether it is a 100 centimeter square area or 1 centimeter square area, I0 would be always at the same point, always would be at this point. That means the exchange current density, I am talking about density with the unit is ampere per centimeter square, that will be same whether it is a 1 centimeter square, 1 centimeter square. So, I0 hydrogen over platinum would remain same. So, then if we try to see the effect of that area change over this E versus small I plot, that means the current density plot, will not be able to express it properly or will not be able to do it. So, then what would we like to do, or what should we do? Now, let us see what happens if we consider the Tafel equation. I0, I by I0, this is valid for A or C, and this is A or C, and this I0 is corresponding A or C. A means anodic and C means cathodic. So, I consider this to be a generalized equation I0. We are saying that this I0 does not change, and in fact, if I0 does not change with the area, then if the area we consider, that line would also follow this particular track, because we are always considering current density, and then always will come across this point. So, this particular that means the addition of those I0s also will be following this particular green track. So, we will always come across this particular E mix and I core, which is current density. Remember, this plot is about current density. Now, how do we attack this? So, now if we try to modify this equation by considering the area. So, let us say I consider some area A. So, if I multiply area on both sides, denominator as well as numerator. So, both side if I multiply, so then equation, this particular equation will turn out to be capital I by I0. So, because we are multiplying the same area for both the current densities. So, this equation should be equally valid. Now, if we try to plot instead of log small I, so that means if we try to plot log capital I instead of log small I, we will be able to understand that this particular corrosion event of the active component because of the increase of area of the cathodic part. So, in that case what happens, the I0, so this and I0 hydrogen over platinum, this is capital I0 and small I0, they will be different, because in case of let us say I0 hydrogen over platinum, if it is 10 to the power minus 5 ampere per centimeter square. So, then I0 hydrogen over platinum of 1 centimeter square would be 10 to the power minus 5 ampere, but I0 hydrogen over platinum surface, if it is 100 centimeter square, it will be 10 to the power minus 3 ampere. So, then I could see that this particular point, if this plot becomes instead of small I, if it is capital I, this shifts to the right. And interestingly, that will explain the rapid corrosion of the active component when we connect active metal with a noble metal, and the noble metal area is higher than the active component. So, let's stop here. We will continue our discussion on this particular issue in our next lecture. Thank you very much.